Hi guys, this video is on the first section of chapter 6. We're talking about Gibbs and Helmholtz energies. What these are pretty handy. But they allow us to predict whether or not a process is spontaneous and also figure out the maximum amount of work that can be done by a process. And another thing that's nice about these is that they depend only on properties of the system, not the surroundings. So I'm going to start with the Clausius inequality that we developed in the last chapter, chapter 5. And it just says this right here, that temperature ds is greater than or equal to d bar q. If it's a reversible process, then the equality holds and it's equal. But, okay, we can write d bar q another way. Because we know from the definition, well, not definition, from what internal energy is, that du is equal to d bar q plus d bar w, or d bar q is equal to du minus d bar w. If we just substitute this expression right here in for d bar q, we get this. TdS is greater than or equal to du minus d bar w, or rearranging that, TdS plus d bar w minus du is greater than or equal to 0. Now, up to this point, we've only really looked, for the most part, at expansion work or PV work. But work that's done on or by the system can also be non-PV work, like electrical work, stuff like that. So we're going to take that into account. So this d bar w, we're going to write as the non-PV work and the PV work. So PV work, we're going to write as negative P external dV, constant pressure. And the non-PV work or expansion work we'll call d bar w non-PV. So writing this term as the sum of these, we get this expression right here. But if we're talking about an isolated system, and we will for now, we know that du is 0, right? The change in internal energy, the internal energy can't change if there's no way for energy to get into or out of the system. And also work cannot be done on or by the system. And that means that all this stuff is gone basically, and we get the inequality that TdS is greater than or equal to 0. But temperature can't be 0, Kelvin's, right? That means that ds, change in entropy, has to be greater than 0 or equal to 0. Now we're going to start holding some variables constant, t, p, or v. And when we do that, just remember, because we're talking about state functions here, for a variable to be constant, it only means that it's the same in the initial state and the final state. It can change in between as long as it ends at the same place that it starts. It ends at the same temperature that it starts at, and etc. So let's first look at an isothermal process. So the temperature is held constant because at constant temperature, dTs equals TdS. T is constant. Can pull out of the differential. And we write this from up here, TdS minus du, right here, is greater than or equal to, we'll bring this stuff on the other side where this is the PV work in this term, negative that is. So we get negative d bar w PV plus d bar w non-PV over here. And what we can do now is we can write TdS as dTs. That's what we said, that's why we said this over here. And so what we get is du minus ts, we multiply both sides by a -1 here, is less than or equal to d bar w PV plus d bar w non-PV. You'll see why in just 1 second. So this is where we're at, guys. So we're going to define a new state function, symbol capital A, and it's called Helmholtz Energy. And it's defined as being equal to the stuff in the parentheses here, u minus ts. So now we can write this, okay? Remember, this is an isothermal process at this point. For that to be spontaneous, the condition is that dA, bring this over to the other side, minus d bar W PV plus d bar W non-PV is less than or equal to 0. And if it's a reversible process, then the equality holds. So Helmholtz Energy talks about isothermal process, both kinds of work, PV and non-PV. The maximum amount of work that can be done on or by the system for a reversible process is the sum of the two types of work, which is equal to, when it's reversible, dA, differential of the Helmholtz energy. So we get this expression right here. So that's useful because if we're talking about an isothermal process and both types of work can possibly be done, then the maximum amount of work, usually we care about how much work can be done by the system, is equal to, we can get that from the Helmholtz energy. So, little example. We're going to calculate and compare the maximum amount of work possible done by the electrochemical oxidation of two compounds, methanol and ethanol, on a per mole basis at standard conditions, so 298.15 Kelvin and 1 bar. And to make it easier on ourselves, we'll assume ideal gas behavior, given this information up here. So this is the heat of combustion of methanol, heat of combustion of ethanol, the entropy, the molar entropy of each of the species involved. So calculate the maximum amount of work possible. Okay, it's electrochemical oxidation, so we're going to use the Helmholtz energy at constant temperature. Okay. From the definition of Helmholtz energy, A is equal to U minus Ts. Constant temperature, take the differential of both sides, basically integrate. We get the delta A equals delta U minus TdS. But we also know from previously that delta U is delta H minus delta PV. So if we substitute this, well, actually one more step, and delta PV is delta N RT. Isothermal process, temperature is constant, or is a constant, so it's just delta N. So if we substitute this in for delta H, we get this expression right here for the change in Helmholtz energy. Delta H minus delta N RT minus TdS. Here, as earlier, delta N is the change in the number of moles of gaseous species between the product side and the reactant side. So product gaseous species minus reactant gaseous species. We'll see in just a second. So we have all this information. Let's go do it. So this is the balanced equation for the oxidation of methanol. You should check, make sure. I'm pretty sure I got it right. We're given the delta H for this process is the delta H combustion because this is a combustion reaction. The difference here is that we're doing it electrochemically rather than using thermal energy to get over the barrier. So delta H for this process, we care about it because of this term right here was given. Delta S is just products minus reactants. So these are the entropies that we were given for carbon dioxide. This is in joules per Kelvin mole. This is water, liquid water. So the 2, because there's a 2 right there, multiply that by 2, minus methanol's entropy, we were given this, and 3/2 the entropy of oxygen, which is that right there. So put those in, we get delta S for this process is negative 80.8 joules per Kelvin mole. And it makes sense that it's negative because we have 1 mole of gas on the right side, 1.5 moles of gas on the left side. So the entropy is going to be decreasing. And so, delta N, can't skip that. Delta N is the number of gaseous products, 1, minus the number of gaseous reactants, 1.5. So the difference is negative 1/2, minus 0.5. All right, so we have all of our numbers. Plug them into this equation right up here, delta H here. Everything here is going to end up being in kilojoules per mole, the way the units work out. Delta minus delta N, negative 0.5. This is R in kilojoules per Kelvin mole. That's a temperature, Kelvin, minus T delta S, I converted the joules per Kelvin mole to kilojoules per Kelvin mole. And we end up with a negative 701 kilojoules per mole. Okay, so that's the change in Helmholtz energy for this process per mole, which means that it's negative, which means that we can do work, and that's the maximum amount of work that we could do by this process, both types, PV and non-PV, at constant temperature, isothermal. And going through the same process for ethanol, this is the balanced equation for the oxidation of ethanol. We were given delta H of combustion, which is our delta H of reaction. We find delta S the same way, products minus reactants, carbon dioxide, water minus ethanol. That's supposed to be an L right there, and oxygen. Plugging those in, I get this. Once more, it makes sense that it's a negative change in entropy because we have 2 moles of gaseous products, 3 moles of gaseous reactants, so the entropy we expect to decrease, and it is. Plugging all these numbers into our expression for the change in Helmholtz energy, we get negative 1,323 kilojoules per mole. So 1 mole of ethanol can do on the surroundings at most 1,323 kilojoules, more than methanol. Okay, so that's the end of that example. Now we're going to include constant volume condition, isochoric condition, in addition to the isothermal condition. So now this applies if we're at constant volume and constant temperature. Constant volume means that there is no PV work, so d bar W PV is equal to 0. And if, that's what we're saying, d bar W non-PV, the amount of non-PV work is also 0, then we can see at constant temperature and constant volume, both of these terms are 0. We came up with this expression earlier. dA, differential of the Helmholtz energy, is less than or equal to the work. If both of these are 0, that means that it's less than or equal to 0. Delta A will be less than or equal to 0. And what that tells us, guys, is that if the initial and final temperatures are the same for a process, the initial and the final volumes are the same for a process, that process will be spontaneous. This is our way of determining whether or not, one way of determining whether or not it's spontaneous is if dA is less than 0. If dA is equal to 0, that just means you're at equilibrium. It's spontaneous in neither direction. It's sitting at equilibrium. Now, we're going to look at a different set of conditions, isobaric and isothermal. So constant pressure and constant temperature. So at constant pressure, dPV is equal to P external dV, pressure is constant. dTs, constant temperature, is equal to TdS. And so from earlier, we already developed this expression right here, TdS plus d bar W non-PV minus P external dV, which is the d bar W PV minus du is greater than or equal to 0. Rearranging this, we get d bar W non-PV is greater than or equal to du minus becomes a plus, PV minus becomes a plus, minus TS, plus becomes a minus when we move it over. But, this is nice because within these parentheses here, we have what's defined as the enthalpy. We defined enthalpy earlier as being equal to U plus PV. So if we substitute H for these first 2 terms here, we get this, d bar W non-PV is greater than or equal to dH minus TS. That looks a lot like we had earlier, which means it's probably time to define a new state function. We'll call that one G for Gibbs. It's Gibbs energy, sometimes Gibbs free energy. And the definition of Gibbs free energy is H minus TS, enthalpy minus temperature times the entropy. Plugging that in here, we get the condition for the maximum amount of non-PV work we can do from this expression. So it gives us d bar W non-PV right there is greater than or equal to dG. If it's a reversible process, that means it's equal, and that's going to be a bound, the maximum amount of work that we can do. Again, this is okay. So the things to get out of this are Gibbs energy talks about constant pressure and constant temperature. So it gives us a bound on the maximum amount of non-PV, non-expansion work that a process can do. So let's revisit that ethanol that we just looked at a few minutes ago and calculate the maximum amount of non-PV work that can be done by the same process, electrochemical oxidation of 1 mole of ethanol, same temperature, same pressure. So this is how you use Gibbs free energy. The maximum amount of work, non-PV work that can be done is equal to delta G, which is delta H minus T delta S. Constant temperature, constant pressure, remember. We know delta H, we were given it in the first problem. For ethanol, minus 1367 kilojoules per mole. And we had calculated delta S, negative 138.7 joules per Kelvin mole. So if we substitute into delta G equals delta H minus T delta S, delta H minus T delta S, and again in kilojoules per Kelvin mole, we get negative 1325, 1326 kilojoules per mole. Okay. Remember, so what this is, what this tells you is the maximum amount of work of non-PV work, non-expansion work that can be done by the electrochemical oxidation of ethanol in this case. But remember, okay, we calculated delta A for the same process and we got negative 1323.1. Not quite the same. That tells us something. Remember that delta A is the PV work plus the non-PV work. Delta G is just the non-PV work. So if we take the difference, you guys, between delta A and delta G, it looks like this. Delta A minus delta G, WPV plus W non-PV minus W non-PV is just the PV work. And that means that minus 1323 minus 1325, again, we just got these numbers, is equal to positive about 3 kilojoules per mole. What that tells us is this, is that the amount of PV work that happens in this process is first it's positive, which means it's done on the system, and that makes sense because we have fewer gaseous products than we do reactants. Right? So so PV work will be done on the system, and also this is the more important point, is that that 3 kilojoules compared to 1,300 kilojoules, it's negligible, right? So the amount of PV work that's done, or excuse me. The amount of total work, I should say, not non-PV work. So let's get this. Gone. So this should read work. And there we go. So finally, for this section, spontaneity and delta G. If there is no non-PV work possible, the condition for spontaneity at constant pressure and temperature, that's delta G, is that dG is less than or equal to 0, or delta G is less than or equal to 0. Again, for an irreversible process, that means it's less than 0. Reversible process equal to 0. Remember, the stuff we talked about in Chapter 5 still holds true. The true requirement, really what's going on, is that for a process to be spontaneous, the total change in entropy must be positive overall, which is delta S of the system plus delta S of the surroundings. But we can see that in our delta G here. If we take our definition of delta G, delta H minus T delta S, and just divide both sides through by T, we get this right here. So remember this, we're talking only with delta G and delta A about the system. So this is delta H of the system, delta S of the system, and we know that delta S of the surroundings is equal to negative delta H of the system over T. So if we plug that right here, we see the same criteria. That negative delta G has to be, has to be less than or equal to 0, which is what we said here. And there you go.